All right, good evening, everybody. I hope you're ready for some robots. So today I will be talking about intelligent flying multi-robot systems. So that's a pretty long title. And I'm pretty lucky because I'm the first one in the series where I'm going to talk about robots. And I want to use that opportunity to simply also talk about the relationship of robotics and AI. And so robotics is quite often also in the literature, I would say. So here on the left, some video about Waymo, which is maybe the first company that succeeded in something one could call self-driving cars and ride-hail services. Quite spooky if you ever go there, if you see those things. And then on the right-hand side, you see a recent breakthrough by Google and also some people from TU Berlin, a system called Palm-E that combines large language models with robotics. And you can give the robot some command like pick something up, and the robot will maybe do it for you. But then we also talk about flying robots here. And so, of course, before we dive into what I do, maybe we should also take a look what's possible with flying robots these days. And so here on the left, you see, again, a commercial system, which was released maybe 1 or 2 years ago, of a self-driving drone that you can just launch from the palm of your hand, and then it will start following you. And on the right-hand side, you see also a recent breakthrough, but more on the research side, where the automated system reinforcement learning beats human FPV drone racers. Okay, so what about multi-robot systems that also existed in the title? Well, multi-robot systems are not that apparent if you walk out, but every time you order some stuff online, for example on Amazon, there are a lot of robots that play a role. They run around in these sort of warehouses and bring the items to humans, and the humans are then the ones who have to pack the box and ship it to you. But they operate thousands of robots in single warehouses and are maybe the largest companies that has these multi-robot fleets available. So why don't we see more robots in general? So there's many open challenges, some of which I will address today. But maybe one of the most important one is safety. That's why self-driving cars are still not here in Germany. It's also very tricky to do fine manipulation tasks. That's why Amazon uses the robots to bring goods to humans to pack, but the robots don't pack for us. And finally, the coordination between robots turns out to be quite tricky. And that's also where my research comes in. Robots are expensive, but if they would solve more problems, the price would most likely go down. And so ultimately, what we are here at BLISS about today is, I think we need more advancement in AI in general to get the robots out there and to help us. Okay, and so in today's talk, I basically will talk about two different aspects of safety that are most relevant for flying drones or teams of flying drones. And so the first part I'm excited about is what will happen if you put multiple drones in a small volume. Like imagine a room like this, and we want to have a few hundred drones flying. And so we tried to look at what would happen if we do that. And it turns out that you have quite some problem here, because if you fly in close vertical proximity, you get something that is known as a downwash effect, where the upper robot influences the lower robot negatively. And this force that we can actually measure in practice is quite significant. So in particular, we have these drones that just weigh 30 grams. And if we fly just half a meter apart, then we already get magnitude of 9 grams, which then results in these big differences. And so the question is, can we somehow model that? And also, can we then improve the flight performance, of course? And to this end, we, of course, want to use machine learning to just approximate this effect. And to understand how we can do that, we have to look a little bit at the dynamics. So each of these flying vehicles can be basically modeled as a rigid body in space. And the residual force will kind of depend on what the neighbors are doing. So if I have one other robot flying above me, the force is going to be larger compared to the case where it's maybe flying to the right of me. And so what we used in this work is a pretty old technique called deep sets. And the deep sets have a very intuitive explanation. So from a technical point of view, there are just two neural networks that interact with each other, and we learn both of them. And intuitively, if we look at an example where we maybe have handwritten digits and pictures of them, and our task is to just compute the sum of what these digits represent, then one neural network might take each of these pictures and tries to predict what the real value of the digit itself is. And the outer neural network tries to combine these latent representation. So in this very simple case, the combination would be just a sum. And this is a very powerful method because the neural networks can be very small. And so we can run both training and inference very quickly. We also extended this to deep sets. And in deep sets, the idea is that maybe not all of the pictures are of the same kind, but maybe we want to combine pictures and something else. In our case, small robots and big robots. And then we can also find an approximation that very efficiently learns just a handful of neural networks, namely k plus 1, 2k networks, just in order to deal with these different groups. And then in terms of data collection, it's actually not so difficult. So what we want to do is just supervised learning. In supervised learning, we unfortunately need labeled data, and we have to compute the labels. And in this case, it might be unclear how to do it, but it's actually that we just look at the difference between our nominal model, what we know from physics what should happen, and what we can measure. So on each of these flying robots, we have an accelerometer that can measure the acceleration. We can also use a filter to predict where we are in space. And then we can combine all of these measurements to compute the difference between what we have measured and what we have predicted. And that is known as a residual force in this case. And then ultimately we collect a data set that tells us for all these relative positions between the different robots that we have, how does the residual force actually look like? And here's just some example. So we flew many different combinations of small drones, big drones, just in some sort of random formation. And then we can basically compute, we can train the neural network, and then the inference can run on a very small microcontroller. And just to give you an idea on how small it is, it's a computer that runs in this 168 megahertz and has less than 200 kilobytes of RAM. So totally crazy if you think about modern architectures used for training, but inference can be done very quickly, and even training can be done on a regular CPU. And then we care about safety because it's flying robots, and if we just learn something random and then apply it, then the robot might crash, which in the best case is just expensive and time consuming, but in the worst case, we harm humans. And so in robotics, we care a lot about stability. And stability intuitively means, can we handle some sort of disturbances that happen and not crash at the end and go to our target reference? And we can actually show that we can train a neural network that we use in this way and still have stability. And the way we do it is that we, on one hand, limit the magnitude of what the neural network can output. And on the other hand, we limit how crazy it can oscillate between different inputs, which is also known as Lipschitz continuity. And we can use a technique called spectral normalization during training that limits this Lipschitz continuity. And then if you do that, then we actually get a control performance that is significantly better compared to before. And that is true across like different settings. So even if you have now multiple drones, you can kind of improve the performance. You still see like this kind of little vertical motion, but that is mostly because our robots have very limited actuations. And so the forces we would need to compensate for are so large that our motors can't handle it. And across many different kind of settings, we can just show that these maximum errors that we get in terms of tracking is just reduced significantly compared to like a state-of-the-art nonlinear controller that people would use in the regular setting. Okay, and then once we solve this sort of problem, we can also do like things that maybe weren't even possible before, like these very close proximity flights where we get not only horizontally very close, but also vertically. And just to compare to kind of maybe the commercial systems, many of you might have seen these sort of drone shows where we use drones to replace fireworks. But in these cases, you can really avoid this downwash effect because you can make use of the human perception not being very good about depth. So you can just put some drones here, some drones behind. Humans won't notice, the drones are happy. So it's actually quite amazing that we can fly that close with this trick. And so we also tried to do the same thing with just the baseline, and then of course that just resulted in crashes in our case. Once we have learned a neural network, we can also use that just to kind of visualize it and try to understand what is actually happening. And that, of course, goes maybe in like is also the direction of explainable AI or explainable physics, because we use these kind of data-driven machine learning tools to gain insights into something. And in this case, this downwash effect, we still don't know. We have no real way of modeling it. Even with like fluid dynamics, it's very, very difficult. And so this is kind of cool that we were able to like visualize these interactions and that we can predict them even in larger teams of like, let's say 2 or 3 robots. And then what you maybe also have noticed is that in terms of artificial intelligence, it was not only key to just understand supervised learning, but we needed to use a lot of different tools. So in this case, we needed to understand control theory to prove stability. And it was also very challenging to just collect data and run the experiments, which required a lot of actually embedded programming with these microcontrollers. And so this project is something I've maybe worked on like 2 or 3 years ago, more like 3 years ago, 3-4 years ago, actually. And we wanted to extend it and just say, okay, now we have this great model. Let's just use it for planning and come up with plans that where the robots do amazing things. And it was supposed to be like a little 1-week project, and I'm still working on it. And so in kind of the rest of the talk, I will try to explain why is it so difficult and what can we do in order to do these sort of planning these learned models more efficiently. And so this is a more recent work that was also just presented by one of my PhD students. And so we tried to look at a very fundamental problem in robotics, which is just how do you get some robots from A to B? And you're given a lot, you're given a representation of your environment, you're given how the robot behaves, a dynamics model, and you're given a start and goal. So it seems like we're in 2024, that is a trivial thing to do, right? But it turns out it's actually quite difficult. You can see on the left and in the middle some sort of the baselines, especially the left one, which is the most frequently used algorithm, struggles quite a lot computing solutions that I would call reasonable in any way. And so our approach basically combines ideas from continuous optimization and discrete optimization. And so what we do is that we try to decouple this planning problem that is already difficult for a single robot and try to do it for each robot individually. And formally, this is done doing actually a tree search for each of the robots. Then in the second step, we try to identify what are problems that arise just by the robots being near each other and trying to coordinate. So in particular, what are the collisions that are now created because we planned individually? And that is also known as a high-level tree search. And then finally, in the third step, we try to fix some problems that we created in order to make the first two steps more efficiently using nonlinear optimization. And because that is very abstract, I will just try to guide you a little bit through how this is done. So in the first step, we really just basically sequentially or in parallel compute what the individual robots do. And if you looked at the animation closely, you saw that sometimes there were weird jumps of the robots. And that's on purpose because we use offline pre-computation in order to have some short valid motions, and then we just stitch them together and we allow that there are jumps. Then in the second step, we basically simulate what would happen until something bad happens. And then once it happens, we try to identify it and impose constraints. So in particular, we say whenever there's a collision that makes a conflict, and we kind of remember which robots were involved in the conflict, at what state were they, and what time step did it happen in. And then in our search, we constrain, we look at two variants. The first one is we say, okay, the first robot can do what it has always been doing, but the second robot should kind of avoid the state where the conflict occurs. Or you do the other way around for the other robot. Very primitive method, but we can show nice theoretical properties. And then if you do that, then you get this very kind of jerky looking motion for the two robots. And then we do nonlinear optimization in the joint space to get a good result. And that maybe sounds a little bit like cheating, but remember also from machine learning that optimization is very powerful as long as you have a good initial guess. Coming up with the initial guess is the hard part. And so here we use discrete optimization to find an initial guess and continuous optimization to just fix up the mistakes that we made. And then just to show you kind of what we can solve compared to also baselines, again, very simple looking scenarios, but it turns out that most of the state-of-the-art algorithms can really not handle it really well. And we also managed to kind of do scenarios now that no other algorithms could handle. Okay, that's great. What does it have to do with flying robots? Well, once you have a motion planner, you can use it on a team of flying robots and just execute it. And so in this case, it's still kind of simplified, so kind of happening in 2D, but the setting is quite difficult because you have many robots, there's a narrow passage, and you have to coordinate which robot is allowed to enter the narrow passage when. Okay, so I think this is like interesting because it really connects this discrete and continuous optimization, but also from an AI perspective, you have seen here that a lot of tools were used, and none of the tools that are maybe traditionally associated with like modern AI, right? So it's kind of very old school stuff. So informed search, some efficient data structures, nonlinear optimization, and also a bit of theory. Okay, then the big question is now what happens if I somehow connect these robots? So instead of having them operating individually and they only interact whenever there's a collision, what if I just physically kind of couple these robots? And a concrete task could be, let's say I want my robots to help with some sort of constructing something. Like, for example, we want to put this pillar on top of these blue boxes just in order to build a bridge. Then as humans, we kind of know there's like a few steps we have to like maybe take off. Then the robots have to coordinate so that they rotate, that they can go through the narrow passage, and move through it, and then they have to align themselves with a target or orientation. And then ideally, we don't want to manually define it, but we want to automatically do these sort of things. And so the challenge here is that we actually suddenly deal with a very high dimensional coupled state space. So typically that regular model we use for flying robots is at least 12 dimensional. It's like the position and orientation and the derivatives of it. And then we also have whatever we try to carry, which will have another 6 or more dimensions. It is nonlinear, so all of the nice theory we learn, at least in undergrad, is not really applicable. And then we also operate our robots very close to the operational limit. Because we want to carry something, our motors will saturate at some point. And so what we do in here is that we, again, try connecting different techniques that have been around, but not maybe quite in this way. And so we use this hierarchical approach where we first try to sample, but only in the geometric space to really figure out how should the robots be orienting themselves to solve the problem. We use this to warm store the nonlinear optimization in the full state space. And then we execute it on a controller that is actually fully aware of its surroundings and the obstacles. And so if you do that, you get kind of these sort of things. And maybe I will just try to show you how it looks like. So it's like this forest-like environment. The red line is really showing us kind of the nominal values. And then the green thing is if we do a full simulation, what would actually be happening. So this is again like an offline planner. And then we can, once we have planned, we can execute it on the real robots. So here's one example that we have flown with 3 UAVs. Unlike many other people, we also show the takeoff because it turns out that taking off with a payload is actually the hardest part of the whole problem, not really the flight itself. And then we do this reconfiguration to fit through the space, and we move slowly over and land. And so we have many of these settings. This is again more like a forest-like setting. The robots really have to navigate through these areas, and we have to avoid these cases where maybe one robot decides to move to the left of one of these trees and the other two to the right, because then the cable would collide with the rest. Okay, and then again, like maybe we can agree that it's AI, but it's also not this traditional or this modern AI with machine learning. But we have used here things like randomized algorithms, nonlinear optimization again, convex optimization that is actually running on board the robots to do the collision-aware planning, and a bunch of control theory for this onboard controller as well. Okay, so that was basically everything I wanted to say about just how can we fly safely, where safety basically means stability and also collision avoidance. The other important thing we should not forget is that whenever we deploy robots in the real world, there will be many other actors that do strange things to the robot, and we should be aware of this possibility, and we should take it into account during decision making. And so in this work, what I want to talk about is a work where I would say, we basically took the idea of AlphaGo or AlphaZero and put it into robotics. And so if people don't know, like AlphaGo or AlphaZero were like extremely successful because it was this learning-based method that basically managed to beat the human champion in playing Go, which is a very like high-dimensional, difficult problem. But if you think about Go, it's a discrete problem. Like every time you have a turn, you take like one of these stones that you have, and you make a decision on where you want to place it. In robotics, we deal with continuous state spaces and continuous action spaces. So it's not entirely clear how we would be able to like transfer the idea. And so the settings we were interested here are known as adversarial games or reach, target, avoid games. And in these settings, you have two teams of robots, and each team kind of shares like typically an opposite objective. So for these reach, target, avoid games, one team's goal is to go into some sort of target region, which is the green region over there. And the other team's goal is to kind of prevent this from happening. So a very typical thing that you need in surveillance or also safety kind of settings. And so maybe as a background, in order to understand how we solve it, just one paper here, which tries to use the idea of privileged teachers. So let's say we have a problem that we know how to solve in a centralized fashion. So for a team of robots, we know exactly how to solve it. But we want to find policies that can do that in a distributed fashion. Then we can frame it as a supervised learning problem where we use the expert, the centralized expert, to generate the labels. And then when we train it, we just give that policy less information. In this particular example, we just give it the local information of what the sensors might see. And then you can basically automatically synthesize a policy from a global controller into a local controller. So that's one building block we're using. And then the second building block is Monte Carlo tree search, which is also another classic AI technique that basically made AlphaZero so successful. Because what happens in AlphaZero is that it combines machine learning and the search in an interesting way. Monte Carlo tree search is pretty simple. It basically just uses randomized simulations to predict what will happen. If you have this multi-robot or multi-team setting, not much changes. The only difference is that you reason about the potential actions that both players in the game could be taking. And then what Alpha Zero did is basically it used this Monte Carlo tree search, and then it trained two neural networks. One is a neural network that predicts the value. So it kind of tells us for a particular state we are on the game, do we believe that we will win or not? And the second one is a policy that tells us, okay, in this particular state, it seems very likely that if I take this action, that is a good one. And then during the tree search, it basically uses these two networks to guide the search in order to improve the policy. Now, if we want to bring it to robotics, we do exactly the same thing. So we kind of have a learner policy and an expert. Both of them are actually Monte Carlo tree search methods. The expert has access to the full state. The learner has only access to the local observation. Typically, the expert uses many more Monte Carlo rollouts to do a better job, and the learner is a much smaller search. And then very similar to AlphaGo, we use these two neural networks, one for the policy and one for the value function, just to help and guide and steer our search. And then we use a reinforcement learning style training method in order to iteratively improve both the value function and the policy. Yes. And then if we do that, we can kind of show that we get quite good results in these sort of kind of adversarial settings, even better results than controlled theoretic baselines, because they make some assumptions that are not quite true, which we don't make. And then, of course, once you have these sort of decision-making methods, you can actually deploy it to physical robots. And the nice thing here is that it can actually run in real time. So in this case, not on the robots, but kind of on like a regular desktop computer that can evaluate these sort of policies. And here the red team wins because it kind of captured all of the blue robots. Okay, so this one was a bit more of machine learning because we use like reinforcement learning and imitation learning, but still kind of the powerful methods that made it work was this informed tree search or Monte Carlo tree search. Okay, and then this is kind of like a little bit contrived, right? Because we had like control over both teams and we had this artificial setting of trying to figure out what happens. So maybe more interesting is, what if we take a drone like the one I showed at the very beginning that can kind of follow humans and see what would happen if we do weird stuff to it. And that's also another recent work with a student peer in my group. And so here what we try to look at is adversarial attacks on existing learned solutions. And maybe people have seen these sort of examples for autonomous driving cases. If you put funny stickers at the right places, suddenly your autonomous vehicle will like not see the stop sign anymore, but see it as, for example, a speed limit or other sort of things. Similar cases happen with these sort of object recognition. You can like have wear these funny backpacks with patterns, and then suddenly the AI cannot track you anymore. That's kind of shocking, right? So let's now consider the case where we don't do that in a static environment, but where we do it in a dynamic environment. Namely, we allow these sort of funny looking patches to be carried by a drone. and we have control over where the drone is going, and we try to use it to influence the behavior of another drone that we don't really actively have control over. And this is also like a multi-robot setting, because potentially you can have multiple attackers. Each of these attackers can carry up to 2 of these funny looking patches, because they can also rotate in place. And then we can kind of frame it as an optimization problem to kind of compute how the patches should look like, and also how we should use the patches in order to gain control over the drone we try to attack. And on the technical side, this is again just supervised learning. It's so-called white box attack, where we assume that we have access to the weights of the neural network of the drones that we attack. And so here's like the baseline we are interested in. It is basically a neural network that was trained to do these sort of follow me scenarios. So the student is kind of walking in this fairly small flight space, and you can see that the drone is orienting itself. And then also if you move in some direction, it will always try to keep a certain distance. So very similar to these like filming drones that you can buy. And then when we carry out the attack, then of course the idea is that the drone now should do the same thing. It's originally seeing the student, it's supposed to follow the student, but the attacker drone occasionally goes in the way, has this funny looking zebra-like patch, and it manages to basically at least temporarily take control over the drone. And you can actually do more crazy things. So in this example, we do an actual kidnapping where the drone still is just supposed to track a human, but instead it kind of doesn't see the human, but our funny looking patch, and we can just capture it in this little net. Okay, so that's kind of scary, right? Because like at least when we originally maybe trained the neural network in order to do fully autonomous behavior, we didn't really anticipate that to happen. And so it's kind of super important, I think, to remind ourselves that safety is not just something we can think about like in an afterthought, but we have to really consider during the design. And the reason why we do these sort of attacks is also to maybe then help us find methods to make the neural networks that run on board more robust towards these kind of attacks that we think about. And in this case, it was again a little bit more traditional machine learning techniques, specifically supervised learning, and also some optimization in order to define the policy. Okay, so what have we learned today? So maybe one big thing I want to get across is that robotics and AI kind of belong to each other. So on one hand, like the AI is really important for us to drive robotics. But on the other hand, the robotics problems are so difficult that they also create new methods in AI. Right? And one example was maybe this at the very beginning, where the human language model drives the robot. We are pretty happy with ChatGPT. I don't think we are very happy about what robots can do with voice commands yet. And then secondly, also that safety is kind of important by design, which means when we do our machine learning algorithms and we use them, we should have safety already in our head. The second thing I want to say is that we should not mistake machine learning and AI. Machine learning is one technique of AI. If you read a textbook, like some standard modern AI textbook, it has many more topics And we should, when we study these things, not forget that the most successful methods are always a combination of modern AI, machine learning, and classical AI. And most of the technologies in the future work will go in that direction. And then lastly is, you saw I had this fancy title of multi-robot coordination, flying robots, everything. The actual demos I've shown you were kind of lame. And maybe that should also just tell us that we're very much at the beginning of robotics. And of course, we all would like our robots to do useful tasks, or dirty tasks, or dull tasks. But we have many more things to do, and we should go all back to work. I would like to thank many people here, just listed the students, the funding agency. You can find all the papers and more things on the webpage of the lab, which the QR code will lead you to. And I'm very happy to take any questions.
Okay. Thank you so much. So now we open for the Q&A. So if you have any questions, please raise your hand.
What's next?
Okay, I will repeat the question. The question was, what's next? I can only speak for myself. So we have many exciting lineups. So for the very first part of the talk where I talked about motion planning, we actually want to go back to this motivation on planning for robots that where we can fly hundreds of them in a small volume. And that means we need to be able to plan with learned models, not only with nominal models, and everything becomes super high dimensional. And so I would say like 2/3 of my group are actually working just on this topic. We're still at toy problems, but we're making progress. For the other side of safety, adversarial attacks, we actually bought this hover air drone that I showed you at the very beginning. And we have no idea what AI it's using. And we're actually working on finding methods to attack it, to demonstrate that even if you don't know what's inside, you can do evil things. And then hopefully it will help us or other researchers to be a bit more careful with what kind of AI we put out in the world.
One question. Okay, so thank you. This is a very interesting presentation. I had a question about benchmarks, because you have mentioned that you have tested the robots for random inputs, whether they react well to like a random person entering the scene or some random disturbances. And I was wondering if you have like dedicated benchmarks for those coordinated tasks. Like maybe the robots kind of prioritize not dropping the cargo then, or landing in a slower way to, protect it.
Okay, excellent question and a pain point in robotics. So unlike computer vision or maybe machine learning on abstract data sets, we don't really have good benchmarks. And it's a little bit embarrassing because it basically means that every time you go to a conference and there's a new paper, it's typically the first thing these people did was creating their own benchmark and then comparing themselves with usually themselves because it's their own benchmark. And I think the community is slowly working on it, but one big challenge we have is that many of us like to work on real robots. We typically don't use the same robots because the robotic companies go faster out of business than they are founded. So we have whatever robots we have laying around because we bought them 10 years ago or we have developed in our own lab. And that's a problem. But I think there are interesting initiatives that try to create benchmarks for some settings. In simulations, that's less of a problem. So for example, in this motion planning setting, for the multi-robot coordination, we now start having competitions and benchmarks for these sort of problems.
Yeah, thank you very much for the talk as well. Really interesting. I had a question. I think where you used neural networks, you used vanilla MLPs, right? Or like in the parts. And I wanted to ask if you ever did any research on neural ODEs and using that.
I did not, and we mostly use these very simple neural networks because we run it on the microcontroller. So anything complex, we are not that excited about.
I had a very basic question. What vision libraries do you use?
We almost don't do any computer vision.
Yeah, thank you very much for the talk. It was very interesting, in particular for someone like me who did not know a lot about robotics before. And from that perspective, I wanted to ask, because you told that you use many different methods from machine learning, from AI, from dynamical systems, and so on. People working in your lab or working in the field of robotics, what background do they usually have? Typically more electrical or mechanical engineers or computer scientists or, yeah.
I think there's no typical here, and also robotics is often in different departments at different universities. Here it happens to be at TU Berlin, it happens to be Faculty 4, so EECS. There's a little bit of robotics also in Faculty 5, as far as I know. In my group, I'm the only computer scientist. I have one student who's studied actually this like computer security, one student who's like controls engineer, and one student who actually was in a program studying robotics. But these programs, I'm not even sure if it exists in Germany, but there's some universities where you can get a master's in robotics, basically. Maybe that's the beautiful thing about robotics. That's also what has drawn me to it. I could never really decide what should I study. I was always between electrical engineering and computer science. And I really think I've found the right thing now where I can kind of do everything. And it's fun to work with different people. We have totally different vocabulary often, but that's how you learn.
Hey, this is more general question about the field, because one of the questions was, where are the robots? And in case you have heard about the recent NVIDIA's Dr. Eureka, what do you think if this could have like, could this be like a tipping point where now it enables much more robots to be trained and be developed and they're released in the real world?
Interesting problem. I mean, first of all, the level of the stock doesn't say anything, right? That's just market analysts believing something. Right now, there's a big hype around machine learning. I think it's largely driven by the large language models because they are very obviously affecting everyone. Like not only on a fun level, but there are certainly some sort of jobs maybe that are on the line because AI can do it. If you think about robotics, NVIDIA also has invested a lot of effort into robotics. So they have their own team in Seattle, like dedicated researchers work on robotics problems, publish papers. They have a simulator called ISACs that really can simulate robots and also have these high visual fidelity to solve problems. But I believe that all of these things don't necessarily are like the kind of missing piece. Because when you think about like those beginning slides that I had, the things that are missing, some of them also included, for example, manipulation. And in manipulation, I think the limiting factor is not necessarily kind of the AI or machine learning. It's really the physical hardware. Like how, like if you think about a human hand, there's many different sensors and many different actuators. We are not really able to replicate that, even just physically. And that would be a prerequisite to then maybe train an AI to do these sort of things. So that's one thing. And the second thing is safety. Are we really believing that just by using 1,000 GPUs and then training in a simulated, driving maybe in a simulated environment for 10,000 kilometers and then not seeing a crash there, are we then confident enough to put these cars or the robots on the road? And that is largely also, I mean, it's an ethical question, it's a political question, and it's a technical question. And all of these need to be answered to really get a breakthrough in robotics.
Are you scared to end up in a moral dilemma like Oppenheimer related to the probable military implications of your research?
Always. I mean, especially if you work with flying robots, most people just know it from the, like, see drones, and then it's military operations, and that's not good. Does it mean we shouldn't do research? That's an interesting ethical question. I believe what I mostly work on is kind of foundational science. If I don't do it, somebody else will do it. And I think many of the things we like work on and that we solve also have civil applications. So for me personally, a big driving factor is to be more effectively able to do search and rescue after kind of like natural disasters, for example. And unfortunately, we will have more natural disasters coming up. And maybe there's many things we should do about it, but one should also be being more effective about reacting to it.
Thank you for your nice presentation. I was wondering when you learned the dynamics of how one robot influences the downward thrust of the other robot. Is it so independent of the model of the robot? Because I could imagine that some motors just have different curves in how they apply their forces or something, that there's actually some error which is robot specific. So how agnostic is your algorithm or the model you learned there?
Good question. So it's definitely not robot agnostic, right? Like, especially it also changes over time. So these sort of motors we use wear out over time and change their behavior. But it comes down to the traditional problem in machine learning, where all that counts is data. And so we all put all the data we have together and assume it's kind of one model, because otherwise we just don't have enough data to do our training.
On the topic of the two robots interfering, what exactly is the reason for using machine learning for that to solve that problem? I would imagine something similar to, for example, PID control could also perform rather well. What is the reason, or did you benchmark other approaches?
Right. So the baseline we had was a standard nonlinear PID controller that just tries to track. And that one is just much worse. The second part of your question is maybe also why do we even use machine learning to like predict, right? Like we could maybe use something like adaptive control, or we could use maybe more old style, like let's say some sort of regression, right? Instead of maybe a feed-forward neural network. And so For adaptive control, that doesn't really work because adaptive control assumes that the changes are kind of slow. So adaptive control works really well if you, let's say, fly in a wind field and like the wind is constant and you try to estimate it. But what happens here is that especially if you have these sort of swapping tasks, the time where you actually have this high external force is just a few milliseconds. So we are looking at like at 10 milliseconds where this force occurs, and then suddenly afterwards and before there's nothing. The adaptive control is out. People have tried modeling these sort of things with more classical methods. So let's say try to fit some sort of functions or insights from physics. There's some people who try to use these kind of fluid dynamic iterations to see what happens. And to some extent they succeed, but at a very high computational burden. So it's not something you can really run online on a microcontroller. And that's maybe where learning is good. Like we shouldn't forget learning is just function approximation. So what we're doing is we're building a lookup table that we can query very, very quickly.